Okay, so let's continue for our chapter for statics for revision. So let's go through for number one. Okay, number one. So state the condition necessary for a body to be in equilibrium. Okay, as we discussed from the previous video, if the body is in equilibrium, it means that it is in stationary condition. Okay, so if the body is in stationary condition, it means that there is no translational motion and there is no rotational motion. If there is no translational motion, it means that the resultant force acting on the body is actually zero. And the second one, the resultant torque about the axis of rotation is actually zero. This is the condition and requirement for the body to be in equilibrium. Okay, so let's move on to B. A uniform ladder AB of a length of 10 meter and weight of 50 Newton is resting against a smooth wall. So length LAB is actually 10 meter. So the weight is actually 50 newtons. So it's resting against a smooth wall. Okay, this smooth wall is actually a keyword, and the resting against a smooth wall, it means that the ladder is actually in equilibrium. Okay, draw and label the forces acting on the ladder. Okay, let's say I have my wall here and I have my floor, and this is my ladder. Okay, so since the question doesn't mention anything about the wall and the floor, okay, I missed something missed some information, which is the angle between the floor and the ladder is actually let me see, is actually 40 degree. Okay, so this one will be my angle, and this one is A, and this one is B. Okay, so since the question doesn't mention anything about floor, so we directly know that this is actually a resultant force, which is RB. Okay, so the problem came from here, which is point A. Okay, so let's say this is my wall and this is my ladder. So okay, suppose there is a friction between the suppose this should be our resultant force, which is slide down. Oops, I should draw it more clearly. Okay, this is my wall and this is my ladder. Suppose this RA should be same as RB, which is pointing towards like that, but from this, in this case, the normal reaction between the ladder and the wall should be this one, which is perpendicular to the wall. This is because since the question mentioned about it is a smooth wall, it means that it is frictionless between the ladder and the wall. So there is no friction, it means that there is no horizontal component of the force. Okay, so this left only the vertical component of the force, which is the normal reaction. So this normal reaction basically will give us the RA, which is perpendicular to the wall. So this one will be our RA. Alright, so this one should be RA. Okay, let me erase this one. So this will be our final answer. Oh, I missed something, which is the weight at the middle. Okay, so let's move on to part 2. So calculate the magnitude of the force acting on the ladder at the end of the A. Okay, so the question asks for the normal reaction A. So since there's no anything information about point B and RB, so we can take this B as a pivot. Okay, so let me draw another diagram. So let's say this is my ladder here. So we inscribe this ladder in terms of rotational motion, which can either be anti-clockwise or clockwise. Okay, as we observe from this diagram, we can see that if this RA, which is pointing towards here, and this weight, which is pointing downwards. Okay, this as we inscribe in terms of torque is actually described about rotational motion. So if we have the force, which is RA, so this force RA will basically give us the rotational motion for anti-clockwise direction. As for the weight of the ladder, so this force will basically give us the clockwise direction if we inscribe this ladder in terms of torque, which is rotational motion. Okay, so since this ladder is in equilibrium condition, it means that clockwise is actually equal to anti-clockwise. Okay, so this RA, from here we can see that, so this one should be 10 meter. Okay, so for clockwise, this one which is the weight of the object, so which is 50. So the perpendicular distance for the weight from B to the weight here, so here to here, from point B to the weight is actually 5, okay, 5.0 sine 40. Okay, let me explain how 5 sine 40 come. Okay, so this is the ladder and this is my weight. Okay, so this, we know that the weight is at the middle of the ladder, so this one should be 5 and this one is B, so this is 40. What we want should be this one, so X is actually sine, okay, sine 40 is equal to sorry, wait, okay, let me, oh, I'm sorry, not sine, should be cos. Cos 40 is actually cos equal to adjacent divided by hypotenuse. So X is actually 5 cos 40. Okay, 5 cos 40, and this one is also 5 cos 40 is equal to the anti-clockwise direction, which is RA. So this RA and the perpendicular distance from A to the floor is actually 5 cos, oops, not 5, should be 10. So this is 10 sine 40. So from here, as we observe from the diagram, what we want is actually here, which is y, and so sine 40 is equal to hypotenuse divided by the is the sine 40 is actually equal to the opposite divided by hypotenuse. So this one, okay, let me write it down. Sine 40 is actually equals to opposite divided by hypotenuse, which is the 10 meter. So y is actually 10 sine 40. Okay, so this is our distance between RA and the floor. Okay, so this RA will basically get 55 cos 40 divided by 10 sine 40. So what we get is actually 29.79 Newton. So this one is 29.79 Newton. So this is for part 2. Let's move on to part 3. Okay, I hope you can see that. Let me zoom it. Okay, so let me okay, erase here. Erase this one and this one. Okay, so question part 3 is actually asked about the force acting on the ladder at the end of the B. So the question is asked about RB. So we know that RB is actually a resultant force which consists of vertical component and horizontal component. Okay, so this RA, so we got RB. So this one should be okay, so RB sine theta, and this one is RB cos theta. Okay, so here it's quite confusing if I draw in this diagram, so I will not draw in this diagram. I'll inscribe in this is in another diagram. Okay, so we know that RB, okay, let's say I draw a plane. Okay, how should I inscribe here? Okay. Okay, so I have a plane. So this one shall be my RA, and this one is, okay, so this one is my RB here. So RA is actually inscribed in this plane, and this one will be my MG, and this one is my RB cos theta. So this one shall be my RB sine theta, which is the vertical component for RB. Okay, so yeah, like that, just like that. Okay, so this one is RA and this one is the weight, this one is the horizontal component of RB and this one is the vertical component of RB. Okay, in terms of equilibrium, okay, so let me just erase this one. Okay, so let me write it down the answer first. Okay, this I erase it's this one. Okay, this one as well. Alright. So if the ladder is in equilibrium, we know that. Okay, let's begin with the vertical component. Vertical force. So vertical force, basically we have RB sine theta is actually equals to our mg, which is 50 Newton. Okay, so this one will be our first equation. So as for horizontal component, so this all forces acting on this ladder. So this forces is what we call coplanar force, as we mentioned from the previous video. So just like so. Okay, this is the horizontal component, and RA, if the system is in equilibrium, RA is actually equals to RB cos theta. So this one will be our second equation. Okay, so 1 divided by 2 RB sine theta divided by RB cos theta is equal to 50 divided by RA. So this can be cancelled, and this one is tangent theta, and 50 divided by 29.79, which is RA. So basically the theta we got is 50 divided by 29.79. So inverse tangent we got 59.2. 59.21 degree. So this 59.21 degree is actually for the angle of RB from the horizontal axis to 1 degree. Okay, so we have this information. Basically we are able to find the magnitude for RB. So let's say I use this equation. So 59.21 degree is actually equal to 50 Newton. So RB finally we got is sine 59.21. Okay, so the final answer we get is actually 58.20. This is how we find the normal reaction for RB. So if the question is quite confusing, we can use the method by redrawing the forces again in this plane, so that we are able to resolve it in, should I say, more easier way for me. Okay, so as I resolve one by one, I'm able to see it and analyze it, whether this force is in either in vertical component or horizontal component. So this is the way we resolve the force step by steps. Okay, so let's move on to the second questions. So let me erase this one. Okay, let me erase this one as well. So let's move on to question 2. Okay. So define the coefficient of static friction. Okay, coefficient of static friction, the formula we know that the coefficient of static friction is actually given as mu r. Okay, so this is the coefficient of static friction, which is mu. So is equal to the static friction divided by the normal reaction. So mu is actually coefficient of static friction. Coefficient of static friction. So Fs basically is the static friction. Static friction. Okay, so R is the normal reaction for our system. So this is the way we describe the coefficient, the definition for the coefficient of static friction. Okay, so let's move on to question part B. Okay, part B. Block A on the horizontal surface of the table is connected to block B by an inelastic string over a light frictional pulley. Block C is put on top of block A. Okay, so this is the block C, and this is the block A, and this is the block B. Okay. So the mass of block A and B. So I have a mass A 4.0 kg and mass B is 2.2 kg respectively. The coefficient of static friction between the block A and the table is actually 0.25. So the coefficient of static friction has no SI unit. Okay, so determine the minimum mass of block C to prevent the block from sliding. So the question asks for block C. So we know that if in order to prevent the block A from sliding, it means that there is no resultant force. Since there is no resultant force, it means that there is no translational force acting on block A. So the block A will not slide down, slide towards right, towards here, which is the right direction. Okay, so if there is no translational motion, as we discussed from the previous question or the previous video, we know that if there is no translational motion, so the resultant force is actually equals to 0. So how can we find the resultant force? So this resultant force, we know that from this P is actually mBg, which is the weight for the block B. So here, okay, so mBg should minus, okay, so the coefficient of static friction. Okay, so Fs is actually equals to 0. So this is the resultant force. Okay, so mBg is actually equals to mu m total g is equal to 0. mBg minus mu m total is actually refers to ma plus mc. So this one is g is equal to 0. So mBg we got 2.2 9.81 minus 0.25, so MA 4.0 plus MC, which is the one we need to find. So this one is 9.81 is actually equals to 0. So 2.2 9.81 is equal to 0.25 9.81, so 4.0 plus MC. So MC is actually basically we get is 9.81, okay, 0.25 9.81 minus 4.0. So basically our mass for block C for the minimum mass is actually given as 4.80 kg. So this is how we find the minimum mass. Okay, so this is the part B. So let me write it here. MC is actually 4.80 kg. Okay, so let's move on to the second parts. Let's move on to part C. Okay. Okay, so let me scroll down a bit. Okay, so this is part C. If the block C is lifted, draw a diagram of the force acting on block A. So this is the first part of the question. So this one is my MA. So we can see that there is a string. So it means that the tension is actually here. So there is a tension which is for the string in order to move the block A to the right side. Okay, so this tension is actually basically came from the block B. Okay, so there's another there's a friction here, kinetic friction between the block A and the floor. So this one shall be our kinetic friction. So this is no more the static friction, and since the block A is no more in static condition, so it is in for this question the block A is actually have the motion. Okay, so this block A has the motion, so this is no more the static friction. Insteadly, it is a kinetic friction. So let me write it down. Kinetic friction. Alright, so this is kinetic friction. Okay, so this is the diagram. Okay, so this is the first part of the question, and calculate the acceleration of the block. Okay, so we have mbg minus so we have this force basically must be deducted by the kinetic friction. Okay, so will be our resultant force. So there is no more MC, so the mass of MC is not required, and this will be our acceleration. Okay, so B. So what is the mass for our B? So this is 2.2 and 9.81. So the coefficient of kinetic friction, okay, so let me write down another formula. Okay, so this is the mu MBG. So this is MA. Oops, this one should be MA. Okay, so this one is MAG. Okay, so MBG is actually 2.2 and this is 9.81 minus the coefficient of kinetic friction is 0.20. Okay, so this is MA is 4.0 and this is 9.81. Okay, is equal to 4.0. Is it 4.0? Okay, yes. So this is the acceleration that we need to find. Okay, so the final answer we got is actually, okay, 9.81, okay, divided by 4.0. Okay, so there's a mistake here. So let me find out where is the mistakes. Okay. So which one will be my mistakes? Okay, this one is 2.2, 9.81. Okay. Oh, I missed something here. So this acceleration should be MA plus MB. Since MA and B, block A and block B is moving simultaneously, so this acceleration belongs to MA and MB. So this one should be MA plus MB times A. So this one should be the correct answer. So this is MA. MA should be 4.0 plus 2.2. So this is A. Okay, let me calculate it again. 0.2, 4.0, 9.81. Okay, divided by 4 plus 2.2. Okay, so the final answer we got is actually 2.215 milli per second square. Okay, this is how we answer the questions. So this is how we find the acceleration. So need to understand, need to be note that this is actually MA plus MB since the block is moving together. Okay, so make sure to be careful after watching this video and the problem solving. Okay, so let's move on to our last questions. Okay, so number 3. Figure shows a load hanging on the wall and the ceiling by 2 extensible strings. The string that is tied to the wall is maintained horizontally, while the other string which is tied to the ceiling is inclined at the angle of 30 degrees to the vertical. Okay, so let me draw again for this diagram so that you can see it clearly. So this is my object. Okay, this is my object, and this is the tension T2, and this is the tension T1, and between here and here is actually 30 degrees. Okay, so sketch a triangle to show the equilibrium of the system. Okay, so the triangle means the vector diagram. So as we mentioned about the vector diagram for the equilibrium system, by saying that if the system is in equilibrium, hence the vector diagram will show either in the form of clockwise direction or anti-clockwise direction. Okay, so let's say let us draw whether it will come out with the result either is clockwise or anti-clockwise. So we have the object, so this one is mg basically. Okay, so this is my mg, and this is my T2 tension for this string, and this is T1, just like so. Okay, so as we can see that the direction of the forces is towards here, which is anti-clockwise direction, and this shows that the system is actually in equilibrium condition. Okay, so this is the answer for part A. Okay, so let's move on to B. If the weight of the load is actually given as 80 Newton, calculate the tension of the string. Okay, so the tension of the string. Okay, let me redraw these three forces in the plane so that you can see it clearly. So this one is T1, so this is our T2, so this is the 30 degree, so basically this one will be 60 degree. I prefer to use 60 degrees since it is, for me, is more easier to be analyzed. Okay, so this one is the 80 Newton. Okay, so we have two components. For the first component, we have vertical component. So our vertical component, we have, so this T2 can be resolved into two components. So this one is T sine theta, and this one will be T2 cos theta. Okay, in terms of vertical component, we have T2 sine 60. So T2 sine 60 is basically equal to 80 Newton in terms of equilibrium condition. So T2 basically we got is actually sine 60. Okay, so T2 is actually given as 92.38 Newton. So this is for our T2. So as for the horizontal component, so let me write it here. Horizontal component. Horizontal component, we have T2 cos theta. If it is in equilibrium condition, T2 cos theta is actually equals to T1. So T1 is equal to 92.38 cos 60 degrees. 92.38 cos 60. So basically our answer for tension 1 is actually 46.19 Newton. Okay, so this is how we find the tension of both strings step by steps by analyzing into vertical component and horizontal component in terms of representation of this plane diagram. Okay, so this is how we find and answer the questions for these questions. Okay, so that is all of the questions. So I hope you understand after watching this video. Okay, if there is any question need to be asked, please comment on this video below. So I'll see you in the next video. Okay, thank you. Bye.